Hello and welcome to C++ Weekly. I'm your host, Jason Turner. I'm available for code reviews and on-site training. Now, in this episode, I am going to show you how to get expert level C++ knowledge. So be sure to stick around and watch the entire episode. I just wanted to make sure that you're aware that every single video description has links to upcoming events, important information about this particular video, how to buy any of my puzzle books or my best practices book, how to hire me for training, how to become a patron, how to support this channel in general. Now, I want to be very clear because I know there will be many misconceptions here. I am not saying that if you understand everything in this episode and follow through with everything that I say, that you will be an expert in C++. What I am saying is that you'll have expert level C++ knowledge if you follow along with all of these topics. It takes years of practice, generally, to actually become an expert in anything. Knowing all about the thing is not the same thing as knowing how and when to appropriately use all of the tools and features of that thing. So the premise for this episode, and I plan to demonstrate this exhaustively, is that if you understand everything about a C++ lambda and how it is used in the language, then you understand virtually every topic in C++. There are some exceptions, of course, and I am going to list those at the end. So I have open here my instance of CLion. This episode is not sponsored by JetBrains, but it is the editor I have chosen to use today. Let's take the most simple of lambdas. This is a lambda that has no captures, it returns no value, it does nothing. At this point, the compiler has generated for us code that looks like this, approximately. So if you can get this far and understand exactly what has happened, then you already have something of a grasp on these topics. Lambdas, structs, const expr, operator overloading, the call operator, const member functions, braced initialization, auto return type deduction, and just kind of generically the idea of compiler magic. Because at this point inside our call operator overload, we cannot see the this pointer of the lambda. And if you understand the implications of that, well, that's an important step in understanding fully C++. Okay, so let's go ahead and add a parameter to our lambda. So now we have a function that takes a parameter. And we need to understand what it means to copy a parameter in C++. But we do have this unused parameter now, which we can mark as maybe unused. And of course, lambdas can take parameters by reference as well. And just in case you haven't been following along, I am live updating the approximate generated code for us along the way. And now we have exposed 3 more topics. Now, all the while, we have been relying on the compiler to automatically figure out the return type of the function for us. But it is possible to specify this with a trailing return type. Now you may be aware that lambdas can actually be implicitly converted to function pointers. And to support this, in our Lambda class, we have to provide some helper conversions. This code now compiles and does what we want it to do. However, it is a bit of an interesting dive into why I actually had to implement the same exact function twice to get it to behave the same way as the C++ lambda. So that's definitely a part of understanding this. So we've just exposed ourselves to class versus struct, which I changed for the sake of convenience, private versus public, implicit conversions, function pointers, static member functions, using aliases, and efficiency when chaining functions, which is why I had to implement this function twice, because there's simply no way for a C++ programmer to have had one function call the other function and get exactly the same behavior when it came to copies. Now, C++ 14 added generic lambdas, which allows us to put auto in our function parameter list. And in this case, the compiler has implicitly created a template for us. And to get this to work, we now needed to have understood templates, template argument, type deduction, and alias templates. And now if we really want to dig into this, we need to understand how the compiler actually created an instance of this template for us. So again, what I'm doing is perhaps a little bit of a hand wave, but in asking for a conversion for this object to this pointer function type, the compiler had to instantiate some templates for us, which would have looked something like this. We don't have direct access to this, but these are things created by the compiler for us. And at this point, I should mention noExcept, which was added in C++ 11 and became part of the type system in C++ 17. Let's go ahead and dial this back a bit and simplify and remove the function pointer conversions. C++ 14 added variadic lambdas, and C++ 17 added fold expressions. And as of C++ 23, we can apply function attributes to lambdas. In this case, we have stated that it is an error in our code to ignore the return value from this function. And we can constrain our lambdas using C++ 20 concepts. And as of C++ 17, we can have explicit template parameters for our lambdas, allowing things like this. I'm sure at this point this all looks like this is getting very complicated, but really the point is just understanding that lambdas allow us to work with every aspect of the C++ language. And I assure you the next example is not going to be any more simple. Let's say we have this tuple of elements. They're all arithmetic types. We want to be able to sum them up together. So I have completed my lambda that calls a lambda that uses an index sequence to unpack a tuple to sum the elements of it and return the result. And the compiler had to generate two different lambdas for us, and it would have looked something like this. But we need to dial this back again and take it back to something a little bit more simple, just the humble capture of a value in a lambda. To capture this integer, our compiler-generated lambda has to actually have its own member called I, and we have to initialize that with something. Now, if we want to mutate this, the code no longer compiles because our member function is const. We can also capture objects by reference, which requires adding a reference member to our lambda, which now starts to raise interesting questions about the nature of references versus copies. Once you understand what the value of I and j are at the end of this function, you understand that concept as well. And once you understand what it means to copy a lambda, you understand the meaning of member copies. Now, C++14 added this notion of generalized captures for lambdas, and they look kind of like this, which means that the compiler had to create something like this for us. And once you understand why the size of your lambda can vary, and why it's not simply equal to the size of int plus bool, and how reordering your lambda captures can actually change the size of your lambda, you start to understand things like object layout, member padding, order construction and destruction. And at this point, I am going to stop showing the equivalent code generated for us, because now we talk more just about how lambdas are used. And if I understand this code, then I've understood a few more things, such as return value optimization, immediately invoked lambdas, guaranteed return value optimization, and initializer lists. Now, the next feature I'm going to show you, unfortunately, this compiler doesn't support yet, but it looks a little like this. Now, this requires C++23's deducing this, but it gives us a way of creating a recursive lambda. So once you understand how to make a recursive lambda, you might understand. Now, this notion of trivially copyable types is an important one, and it comes down to why it's okay to take a copy of the lambda here instead of worrying about a reference in this particular case. And at some point you realize you can return a lambda from a function, and you start to get a notion of higher order functions. And these last few things are not really C++ specific, just general programming concepts that are useful to know about. And in the case where you make a mistake such as this, you learn about dangling references, and undefined behavior. Then you start to reach the next level once you understand how the overloaded idiom works for creating an overload set of lambdas. Now, unfortunately, my compiler doesn't fully support this construct yet either, but I can give it a little help with a deduction guide. So if we understand fully how this construct works, then we now understand inheritance, multiple inheritance, function hiding, variadic using declarations, scoping, and look up rules to see how functions can be found, class template argument deduction, which was added in C++ 17 and enhanced in C++ 20, which is why this code didn't work, because my compiler does not yet fully support the C++ 20 version of this, and deduction guides, which we had to add to work around the missing feature from my compiler from C++ 20. And of course, lambdas really make the most sense when working with algorithms. And now you have some idea about algorithms and ranges. And if you can tell the difference between these different function calls, then you understand the algorithms just a little bit better, and you're also starting to get a little bit of a handle on the functional header. Which brings us approximately to graduation at this point. Once you can write your own implementation of standard function that would be able to compile this code, then I would say you've gotten pretty close to expert level C++ knowledge, because at this point you will have unlocked virtual member functions, member function pointers, special member functions, member function call syntax, type erasure, dynamic versus automatic storage. We're 77 items in so far, and I think this is a pretty good list. Now, of course, there are a few things missing. Unfortunately, to some extent, I guess perhaps what we will have missed is, well, writing your own concepts, but you might choose to do that to simplify the implementation of your function library itself. Type traits, again, might actually be necessary or useful when writing your function implementation. Spaceship operator, didn't cover that. You might be able to make your functions sortable using it. I'm not sure. Protected probably doesn't have a use in your standard function implementation, but it might. Virtual inheritance, I hope you don't need that, because that comes up in the case where you have diamond inheritance, which is rarely a good idea. The general C++ compilation model is kind of lacking from this conversation. ODR violations, one definition rule. Go ahead and Google that if you don't know anything about it. The preprocessor, we've included some headers, but we haven't actually used the preprocessor yet. We haven't actually talked about how to create like an actual large project or anything, so that's definitely missing. The entire breadth of the standard library. There's many different containers, there's lots of things in there to learn. And variable templates got left out. Now there's then a few other things that we haven't talked about. Coroutines, modules. Yeah. I think that mostly covers it. So I don't know, I probably left out your favorite feature, so why don't you go ahead and leave a comment and tell me which one I left out. And hopefully you can use this as a starting point for getting that expert level C++ knowledge that you've been looking for. Thanks for watching. Be sure to subscribe.